So today we're going to start with chemical energetics. Okay, we're going to start with chemical energetics. And the first thing to understand in energetics is the concept of what we mean by a system. So a system, when we say we have a chemical system, okay, a system refers to the reaction or process. Okay, it refers to a specific reaction or process that we're looking at. Okay, so a system is a reference to the actual process that's taking place, and the surroundings, right? The surroundings is basically everything else in the universe. Okay, so if you take the universe, you take the entire universe, right? You're looking at a particular chemical reaction or a particular process that's taking place. We call that particular reaction or process the system, and everything else in the universe is referred to as the surroundings. Okay, so the system plus the surroundings, okay, constitute the universe. Okay, so the surroundings refer to everything else in the universe except that given process that we're looking at. So for example, right, let's say that I have a container, okay, a beaker in which I have hydrochloric acid, right, HCl aqueous, and what I do is I add hydroxide ions. Now over here, of course, if I'm adding, let's say, something like sodium hydroxide, I'll have a neutralization reaction taking place, right, between the alkali and the acid. So I have the following reaction taking place, right? This is the ionic equation for the neutralization that's taking place. This reaction, okay, this reaction is exothermic, okay? It releases heat. We'll just talk about that, okay? But essentially it gives out heat to the surroundings, okay? The reaction releases heat. So these particles that are reacting, right? The OH minus and the H plus, this actual reaction or process that's taking place, right? These tiny little ions that are reacting here, right? This entire process itself is referred to as the system. Okay, and what you would observe in this particular experiment is that the temperature of the water will increase. Why? Because the system is releasing heat, right? As I said, this is an exothermic reaction. This process results in the release of heat. Okay, so what we can say is that the actual particles that are reacting, or the actual reaction itself that's taking place, is the system, and then the beaker or the water surrounding it, right? The solution that we have, the water, the beaker, and all the entire atmosphere surrounding that reaction is referred to as the surroundings. Okay, so it's the actual tiny little reaction that's taking place that is the system. Everything else is the surrounding, including the beaker of water, including the beaker itself, including the rest of the surroundings. Now obviously when we study energetics, we're not going to be looking at the entire universe, so we limit our study to the immediate surroundings, which in this case would be the water inside the beaker. So again, this reaction is taking place inside this, in this beaker, right, inside the solution. Now the reaction itself is the system, right, whereas the surrounding water, right, is part of the surroundings, right. Um, Obviously, the surroundings would be the rest of the universe, but the surrounding water is part of the surroundings, right. And when we're going to be studying this type of a reaction, we're going to be looking at, right, we're going to be looking at the water in which, for example, this reaction is taking place. Okay, so we're going to be looking at the immediate surroundings, or the closest surroundings to this system. So now we're going to define what we mean by the enthalpy change. Okay, the enthalpy change. Right? The symbol for enthalpy change is delta H. Okay, delta refers to change, and then capital H is the symbol that we use for enthalpy. The enthalpy change is the heat exchanged by a system, okay, with its surroundings at constant pressure. And chemical reactions are divided into two broad categories based on the enthalpy change, right? Those two categories are exothermic reactions and endothermic reactions. Okay, So when we talk about chemical reactions, right, they're going to be defined. They're going to be divided into two. We divide into two different categories, right? So we have, okay, look at reactions based on, again, this is a categorization based on the enthalpy change. Okay, the first category that we have is exothermic reactions. Exothermic. So an exothermic reaction, okay, exo means release and therm refers to heat. Okay, so an exothermic reaction refers to a reaction or a system. Okay, an exothermic reaction refers to a reaction or a system, okay, that releases heat. So the system itself is losing heat, therefore the enthalpy change is negative. So an exothermic reaction or an exothermic system, okay, releases heat into the surroundings. Okay, releases heat to the surroundings. Okay. Now again, delta H refers to the heat exchanged by the system, okay, with its surroundings. So if the system is losing heat, delta H is negative. Okay, and Q, okay, the letter Q over here, okay, represents, okay, letter Q represents the heat, okay, the letter Q represents the heat gained by the surroundings. Okay, heat gained by the surroundings, right? So for an exothermic reaction, the system itself is losing heat, so the enthalpy changes, negative, right? And the surroundings are gaining heat, right? The surroundings are gaining heat, so therefore Q is positive. So for such a reaction, the observation that you can make is that the temperature of the surroundings increases, right? Because the heat is being lost to the surroundings, the temperature of the surroundings increases. All right, and then we can also say that in an exothermic reaction or an exothermic system, right? What's happening to the system here is that potential energy is being converted to heat. And in an exothermic reaction, okay, the products are at a lower energy, okay, or lower enthalpy, right, than the reactants. Okay? Lower energy, or more specifically, the lower enthalpy than the reactants. Okay, now in our syllabus, okay, for AS, we're going to be using enthalpy and energy interchangeably, even though they are not the same. Okay, enthalpy is heat is one form of energy, right? Heat is one form of energy. Okay, but we're going to be saying that enthalpy change and energy change mean the exact same thing. Okay, and we're going to modify that understanding in A2, but in AS, enthalpy change and energy change mean the same thing. Okay, so for an exothermic reaction, the products are at a lower energy than the reactants which means that the products are more stable than the reactants. Okay. So in an exothermic reaction, we can say that the potential energy of the system decreases, right? Because it loses, or it potential energy from the system is surroundings. Okay, so the potential energy of the system decreases. In other words, the system is now more stable than it previously was. The other type of reaction that we have, okay, based on when we categorize reactions based on enthalpy changes, okay, is an endothermic reaction. All right. Now, an endothermic reaction, right, we have the opposite. endothermic reactions take in heat from the surroundings, okay, takes in heat from the surroundings, right, which means that the temperature of the surroundings decreases, okay, temperature of the surroundings decreases, which of course means that because heat is being taken in from the surroundings, right, when we talk about the system itself, the system is taking in heat and it is converting that heat to potential energy, right, potential energy, which means that the potential energy of the system increases. If the potential energy of the system increases, it means that the products are now at a higher energy. Yes, products are at a higher energy, or we can say that they are now less stable or more unstable than the reactants. Okay. And of course, if the system is taking in heat from the surroundings, right, the heat exchanged by the system, right, the system is gaining heat, so the enthalpy change is positive, right, and since that heat is taken in from the surroundings are losing heat, so q is negative, right? The next thing we're going to define is the activation energy. Okay, now the activation energy is defined as the minimum energy needed, okay, for it is the minimum energy needed for a collision to be effective, for a collision to be effective. And obviously an effective collision is a collision that results in a chemical reaction. Okay, it is a collision that results in a chemical reaction. Collision that results in a reaction. So you guys should know that from kinetic particle theory that particles are constantly in motion, right? And when they collide, right, those collisions may result in chemical reactions, right? When a collision takes place such that the particles collide with enough energy and with the right orientation, that type of a collision is called an effective collision, right? And the minimum energy needed for that type of a collision to take place is called the activation energy. Okay, so you can rephrase this as the minimum energy needed for a chemical reaction to take place. The symbol that we use for the activation energy is capital E subscript A, right? Now the subscript can be lowercase a or uppercase. You'll see both being used, okay? And you'll also see an effective collision being referred to as a successful collision. Okay, they both mean the same thing. A successful collision or an effective collision are collisions that result in a reaction or a chemical reaction. When we talk about the activation energy, okay, the activation energy, okay, the activation energy is a measure of kinetic stability. Okay, so when we say that they're a measure of kinetic stability, what that means is that the higher the activation energy, okay, the more kinetically stable something is. Okay, the more kinetically stable something is, right? Which means that the less reactive something is. Okay, less reactive. Okay, so when we talk about reactivity, we're referring to kinetic stability. So for example, group 1 metals are kinetically unstable okay, especially when you react them with water, right? We know that in a group 1 metals are kinetically unstable. In other words, they're highly reactive, which means that the reaction between, for example, group 1 metals and water has a very low activation energy. So when we talk about reactivity, okay, when we talk about reactivity, we are talking about kinetic stability, all right? And the activation energy is also the measure of the rate of a reaction, okay? So the higher the activation energy, the slower the rate of a reaction, okay? So when we talk about stability, there's two types of stability that we're referring to. Okay, when we talk about stability, there's two types of stability that we're referring to. Okay, one type of stability is thermodynamic stability, right? Where we're comparing the potential energy of different things. So, for example, in an exothermic reaction, where we said products are more stable than the reactants, we are talking about thermodynamic stability, right? We're talking about thermodynamic stability. That is a reference to the potential energy, okay, the relative potential energy, right? The other type of stability that we have is kinetic stability, okay? Thermodynamic stability is when we're talking about the potential energy of one thing relative to another, and kinetic stability is when we're talking about how easily something reacts or how reactive something is. Higher activation energy is needed for that reaction to take place, which means that the reaction will occur at a slower rate. So now we're going to look at reaction profile diagrams. Okay, reaction profiles. Now, what is a reaction profile diagram? A reaction profile diagram, okay, also known as a reaction pathway diagram. Okay, so reaction profile and reaction pathway mean the same thing. Okay, is a diagram that shows how the energy of the system changes as, or how the enthalpy of the system changes as the reaction progresses. Okay, so on the y-axis, right, on the y-axis we have energy. Okay, sometimes you're going to see enthalpy. Okay, so you can say enthalpy or energy. All right, um, for now we'll just write energy. Okay, but sometimes you'll see the symbol capital H, which is enthalpy. Right, we're looking at enthalpy and energy as the same thing in our AS course. Right, and on the x-axis, okay, we have reaction progress. Okay, reaction progress. Okay, also known as reaction coordinate. Okay, so the reaction coordinate or the reaction progress. Okay, same thing. So we're first going to look at exothermic reactions. Okay, so we're going to look at the reaction profile for an exothermic reaction. So again, on the x-axis we have reaction progress, right? So if we're looking at an exothermic reaction, right, we're going to start with reactants, right? I'm going to use capital R for reactants, right? We're going to start with our reactants, and as the reaction progresses, right, we know that in order for the reaction to take place, there is a minimum energy needed, right? That energy is called, so so here we have the activation energy, right? That's the minimum energy needed for a collision to be effective or for a reaction to take place, right? The minimum energy needed for a collision to be effective or a reaction to take place, right? So this is our activation energy. I'm going to use this symbol for activation energy, right? That's capital E subscript E. Now, as the bonds in the products form, energy is being released, right? So we know that over here, obviously, because it's an exothermic reaction, the products will be at a lower potential energy than the reactants, right? So here we have the products. All right, so again, this is the reaction profile for an exothermic reaction. Okay, there's a reaction profile for an exothermic reaction. The products are at a lower potential energy than the reactant, so they're at a lower enthalpy than the reactants. So we can say that the enthalpy change for this reaction is negative. Okay, The arrow for the enthalpy change will always be shown from the reactants to the products. All right, so the enthalpy change is delta H, and in this case that would be a negative value. Okay, right, so the products are at a lower potential energy than the reactants, right? The system is losing heat, right? Or it's the potential energy is being converted into heat energy, so the potential energy of the system is decreasing. The products are more stable or at a lower potential energy than the reactants, and because potential energy is being converted to heat, heat is being lost, or energy is being lost in the form of heat, so the enthalpy change is negative. When we look at this reaction from left to right, we call this the forward reaction. The forward reaction is exothermic, right? We have this enthalpy change, right, from reactants to products. When we talk about the backward reaction, we're looking from right to left, right? And the backward reaction here would be products to reactants, and the enthalpy change would be positive, right? So we can say that this is the enthalpy change of the backward reaction. Okay, so the general relationship that we have is that the enthalpy change of the backward reaction is simply the negative enthalpy change of the forward reaction. The enthalpy change of the backward reaction is minus the enthalpy change of the forward reaction. Right, so if, for example, if the forward reaction is negative 100 kilojoules per mole, then the backward reaction will be positive 100 kilojoules per mole. And similarly, if we look at the activation energy for the backward reaction, if we're looking at the backward reaction, we're starting with products and going to reactants, and the activation energy would be from products to the top of this hill. Okay, so this would be the activation energy for the backward reaction. So when I say what is the enthalpy change for this reaction, I'm talking about the forward reaction, right? That will be an exothermic value, right? And this will be the activation energy for that one, right? The one on the left, the arrow on the left I've shown. Whereas if I'm talking about the backward reaction, the enthalpy change will be negative that, right? So the forward is exo, the backward, if the forward is, for example, negative 100, the backward will be positive 100, right? And the activation energy for the backward will be from products to the highest point here. So this is the reaction profile for an exothermic reaction. Okay, the reaction profile diagram, or we call this the reaction pathway diagram for an exothermic reaction. Now, examples that we have of exothermic reactions, okay, some examples of reactions that are going to be exothermic are combustion. Okay, combustion of fuel or combustion of substances an example of an exothermic reaction, right? Another example that we have is neutralization. Okay, these are examples of exothermic reactions. Neutralization. And of course, if you're talking about a reaction such as the combustion of methane, so for example, if you're talking about the combustion of methane, you would write CH4, CH4 plus 2O2 gives us CO2 and 2H2O, right? So again, if you're talking about a specific reaction, obviously you'll write the reactants here and the products over here. Okay. So next we have the reaction profile diagram for an endothermic reaction. Okay. Now in endothermic reactions, right, we know that the reaction takes in heat from the surroundings, right? So the potential energy of the system increases, which means that the products are at a higher potential energy than the reactants, right? So again, on the y-axis, we have energy. Okay, again, you'll sometimes see the letter capital H, which just means enthalpy, right? So you have enthalpy on the y-axis or energy on the y-axis, and you have reaction coordinate or reaction progress on the x-axis. Okay, so we have reaction progress on the x-axis. Reaction progress. So we're going to start with the reactants, okay, and we're going to label the reactants, right? For whatever reaction is taking place, you'll write down the reactants here, right? The energy needed for the reaction to take place is the activation energy, right? That will be this guy. That's the activation energy. And then, right, so energy is needed to break the bonds in the reactants, right? And then when new bonds form, you make the products, and that results in a release of energy, right? But in the case of an endothermic reaction, the initial energy needed is greater than the energy released. Okay, so here we have, right, the products will be higher in potential energy than the reactants. Right? Products will be higher in potential energy than the reactants. The enthalpy change for this reaction is positive, right? So delta H would have a positive value, right? So the arrow that we draw for the enthalpy change will be an upward arrow from the reactants to the products. Now again, if you look at the backward reaction, right, for the backward reaction, the enthalpy change would be negative, right? It would be exothermic, and the activation energy for the backward reaction would be if you're going from products to reactants, right? So this would be the activation energy for the, right. But again, when we're talking about the enthalpy change of a reaction, we're referring to the forward reaction. We're referring to the reaction that we see from left to right. Okay, and in this case, let's look at an example, right? An example that we have of an endothermic reaction that you guys have already seen, okay, is thermal decomposition. One last thing to note here is that we can't actually determine the actual enthalpies or the actual energies of different substances. So we don't actually know exactly how much energy the reactants are at, and we don't know exactly what energy or what enthalpy the products have. We cannot determine the actual energies or the actual enthalpies of reactants and products. We can only determine enthalpy changes of certain processes. So if a certain process or a certain reaction releases energy in the form of heat, we call that an exothermic reaction, right, where delta H is negative. And similarly, if a process takes in heat, right, the delta H is positive, we say that the enthalpy change is positive, we say that's an endothermic reaction. Okay, so enthalpy changes of processes and enthalpy changes of certain reactions can be determined, but the individual enthalpies or the actual energies of substances or the actual enthalpies of substances are not known. Okay, the reason we can't determine the actual enthalpy, so we don't know exactly what energy the reactants are at and what energy the products are at. Okay, we just know the enthalpy changes, or we can determine the enthalpy changes for reactions. The reason we can't determine them is because we don't have a reference, we don't have a standard relative to which we can determine enthalpies. Okay, for example, for relative mass, right, relative masses are determined relative to 1/12 the mass of an atom of carbon 12, right? We don't have such a relative standard for enthalpies, and therefore enthalpies of individual substances cannot be determined, but enthalpy changes of certain reactions and processes can be determined.